peut-être aller là-bas.
Bonjour à tous et toutes. Alors, je ne suis pas Gilles Montambeau, comme j'espère vous l'avez remarqué, mais donc Gilles, qui malheureusement ne pouvait pas, il a quelques petits soucis pas graves de santé, m'a demandé de le remplacer aujourd'hui. Alors, c'est d'autant plus un plaisir que notre orateur aujourd'hui, Thierry Giamarchi, je le connais de très longue date, puisque il est venu au labo en tant que thésard de Heinz Schulz il y a presque 40 ans. Et ouais, c'est un petit bail. Et ensuite, après sa thèse brillante et tout, Thierry a continué. Il a été recruté au CNRS. Et après, il était au laboratoire. En fait, il était au laboratoire en face de mon bureau pendant longtemps. Et puis ensuite, toujours au laboratoire, il a déménagé au premier, le traître. Et puis ensuite, après quelques années, Thierry s'est laissé attirer par les sirènes outre-Léman. Il a été recruté à l'Université de Genève et il est devenu au fil du temps à la fois le directeur du DQMP, le département de physique de la matière condensée de Genève, puis directeur du programme MANEP, donc qui est vraiment disons, un gros organisme, enfin un gros moyen de financement de la recherche en Suisse. Et finalement, après toutes ces années administratives, il est redevenu chercheur à part
Simple
entière,
soldat.
soldat, voilà, exactement. Et voilà. D'un point de vue, on va dire carrière, brossé en très larges traits, voilà ce qu'on peut dire. Alors, sur le plan de l'activité, donc Thierry va cliquer. Il
Ah,
suffit d'une chose pour résumer. Voilà,
je précise que je ne sais pas ce qu'il y a sur la photo,
voilà.
l'image.
Donc, Thierry est très bien défini par Herbert Marcuse, qui était donc un philosophe très respecté et connu dans les années 1960 et qui a fait, alors pour ceux qui sont intéressés, regardez sur Wikipédia, une théorie qui est assez intéressante et qui mérite tout à fait le nom. Mais Thierry, lui, j'allais dire, homme unidimensionnel, on va dire, là, on parle de physique, d'activité de physique. La physique des systèmes corrélés en basse dimension, notamment une dimension. Donc ça, c'est le pain et le beurre de Thierry. Il a écrit un livre qui fait autorité sur cette physique unidimensionnelle, mais ce n'était pas uniquement confiné au système organique, au système électronique, aux échelles au-delà. Euh, Également, la physique des atomes froids, c'est quelque chose sur lequel Thierry contribue de façon très active. Et puis, pas uniquement, puisque la physique statistique des systèmes désordonnés, notamment à deux dimensions. Thierry est un des, on va dire, des auteurs très reconnus de ce qu'on appelle le ver de Bragg. Il y a toute une question dans les systèmes, par exemple, supraconducteurs, placés en champ magnétique. Il y a des vortex pour les supras de type 2. Et en fait, quand il y a du désordre, ça peut donner naissance à une phase désordonnée et, disons, qui peut avoir des propriétés assez particulières. Et après le séminaire général, si vous êtes intéressé, Thierry vous instruira là-dessus. Sans plus tarder, je vais lui laisser la parole. Merci Thierry d'être venu.
merci Marc, je pense que vous pouvez m'entendre normalement. Alors on va essayer de basculer sur la présentation. Voilà. Alors j'espère que l'écran est bien partagé. Si vous le voyez, je pense que c'est le cas. Et du coup, ça me permet de démarrer la présentation proprement dite. Voilà, en vérifiant que vous voyez le pointeur. Alors, tout d'abord, je voudrais remercier évidemment Marc, Gilles, qui malheureusement ne peut effectivement pas être là aujourd'hui, et tous les organisateurs de ces séminaires généraux pour l'invitation. Il y avait eu une première tentative, en fait, il y a quelques 6 mois à peu près, puis c'est tombé un jour de grève nationale. Donc, on avait d'un commun accord décidé de reporter à une date qui est celle d'aujourd'hui. Alors, comme l'a dit Marc, dans sa très gentille, mais up to the point, comme d'habitude, introduction, ça fait 40 ans que pratiquement, à une année près, disons 39 ans, que je suis arrivé au labo à l'automne 84 pour démarrer une thèse sous la direction de Heinz Schulz sur les systèmes unidimensionnels, et on va avoir l'occasion d'en reparler un petit peu. Et évidemment, c'est très, je dirais, chargé d'émotions pour moi, à la fois de voir les têtes que je connais dans l'auditoire, et puis d'être dans cet auditoire, alors qui a été un peu rénové, un peu retapé, on va dire, depuis l'auditoire Blandin, où j'ai passé ma soutenance de thèse donc un petit peu plus tard. Voilà. Alors, effectivement, je vais vous raconter. Alors, quand Marc disait je suis un être unidimensionnel, mais c'est juste une question de physique, il ne se référait pas à mon physique, mais à ma physique. Parce que là, je suis plutôt à symétrie sphérique pour ce qui concerne le premier point. Et effectivement, je suis maintenant à l'Université de Genève. Alors, c'est curieux que ça coupe. Bon, mais ce n'est pas grave. Je ne sais pas s'il y a moyen d'enlever la barre qui est en bas. Comme ça, on verra tout l'écran. Mais sinon, ce n'est pas grave, hein. Pas trop s'embêter. Voilà. Je, je reviens. Voilà. Donc, je suis à l'Université de Genève. Enfin, là, vous en voyez la moitié. Et je suis dans le département de physique de la matière quantique, anciennement département de physique de la matière condensée, dont j'ai été pendant un temps le directeur. Et effectivement, comme le mentionnait Marc, il existe une association, c'est un peu l'équivalent d'un LabEx, si vous voulez, qui s'appelle MANEP, Material with Novel Electronic Properties. Et hélas, je n'ai pas complètement arrêté mon activité administrative, puisque je suis actuellement le président de l'association MANEP. Alors, c'est un plaisir, mais c'est évidemment aussi une charge. Et puis, même si aujourd'hui, je ne vous ferai pas vraiment un séminaire de recherche de pointe, mais évidemment, les recherches que l'on fait sont financées par l'équivalent de l'ANR en Suisse, qui est le Swiss National Science Foundation. Alors, je vais basculer en anglais puisque on m'a dit que c'était préférable de faire le séminaire in English. So from now, I will switch to English. So I thank again in English all the organizers of the séminaires généraux. As I said, it's a great pleasure and emotion to be here. The RERB this morning tried to strike again and prevent me from coming, but I managed to do it. Okay. Before we go to the seminar per se, as I said, it's impossible to be here, to talk about 1D here, without mentioning the person, Heinz Schulz, who was my advisor and who introduced me to the beauty of one-dimensional systems, and unfortunately who passed away too soon. And this is the photo you will find probably the most easily. This is one of the very nice photo of him. But I want to share with you a photo that was given already some time ago to me by Patrick Bataille, who is a former member of the lab, and who last week was celebrating his 75th birthday. And it's another view of Heinz. I knew him always like this. And here is a photo a little bit more ancient. So I think it's more for the old people in the audience than the new ones. This is Jean-Paul Pouget, one of the former director of the lab and former head of the physics in CNRS. This is Heinz. At the time when he's there was still dark. And this is Denis Jérôme, whom, of course, many of you know in the lab. I think it's a beautiful photo, and I wanted to share it with you. Voilà, let me go back to the seminar itself. I cannot also resist to showing you my group in the University of Geneva. It's already a slightly outdated photo, but several people are now, for example, Tony Jean has now a permanent position in Université de Nice, but globally, most of the people are still around. And of course, there are many people who shaped my love of the one-dimensional systems. Many, of course, are here, but many are also in other groups in the world, and I would not detail the list. Okay, so let me start this seminar by the content, and I want to go back to materials. After all, we're in a solid-state physics lab, and I think I don't need to insist too much here, but maybe for the more bio part of the lab, that materials play a central role in humanity. You have all ages which have been called after the name of a single material. You have the age of bronze, the age of iron, and so on and so forth. And if we had to name an age for the 20th century, this would be undoubtedly the age of silicon, because this is what existed in the middle of the 20th century. This is the vacuum tube, and the vacuum tube is a very nice amplifier. And with this nice amplifier, you can build a computer. Here is the 1947 ENIAC. Of course, these computers could do what they could do. And here is a quotation from a very serious journal, US journal, a little bit like Physics Today, if you want, in 49 of a person writing a paper on ENIAC and really going wild, you know, in the prediction, saying that where a calculator like the ENIAC has 18,000 vacuum tube and weight 30 tons, the computer of the future may only have 1,000 tube and maybe weight only 1.5 tons. And the thing that changed this totally, you know, crazy prediction and made it, of course, much worse is the invention by these three gentlemen, Bardeen, Bratin, and Shockley, of the transistor. And just for the record, Bardeen is the only physicist who got 2 Nobel Prizes in physics, just for the record. This invention of the transistor started the silicium, if you want, age that we have today. So the question is, how do we master materials? Because it tells you that you need to master materials. And what we understand essentially is free electrons. You all suffered through solid-state physics courses 101. And you all know that we can compute band structures and whatever. But what people usually don't tell you, or tell you later, is that in a real system, even a simple metal, the Coulomb interaction is as strong as the kinetic energy of the electrons. So technically, there is no reason why you should neglect the Coulomb interaction between electrons in a metal, even if there is good screening and whatever, and you should not be allowed to forget about it. So how do we do for the properties of realistic systems when we lose the fact that we solve a one-body problem? Well, the guy who saved us in that respect is Lev Landau, because he has shown that actually, modulo the fact that you redefine trivial parameters like the mass of the particle, you can ignore essentially the interactions among the particles. And this is a beautiful theory, which is called the Fermi liquid theory, and who got him the Nobel Prize in physics. And that sort of allowed people to deal with all the physics of the 20th century in good part by ignoring interactions within materials. This is the fact that you have to redefine the mass and change it into m star. But, you know, who cares? It's a new mass, it's one parameter, and so on. And this allowed then to use free electron theory to understand materials. And then that's fantastic, because you understand where they are metals, insulators, semiconductors, and you can invent the transistor. And just for the fun, I put the Nobel Prize here, year associated with it. You can also understand that you can ignore the very large repulsion between electrons and worry about the very tiny fluctuations of the lattice. And this is what gives an attractive force. And this is superconductivity. Many, many Nobel Prize for superconductivity. And closer to us and to this lab, because this is in this lab that he did the discovery, Albert Fert discovered the giant magnetoresistance, which is the fact that the resistance of a material might vary by orders of magnitude if you change its magnetization or the magnetic field that it is subject to. And these three discoveries are essentially resting very solidly on Landau Fermi liquid theory. I choose those not only because they are, I would say, very, very important fundamental discoveries, but because they completely change our society. Without the transistor, no society of information as we know today. Without superconductivity, a good part of the very powerful magnets that are used in MRI in hospitals would simply not exist. And giant magnetoresistance were used, for example, for a time in magnetic recordings. So they also changed for a while the digital industry. Now, if we move to the future, it's very hard to imagine that we will be forever able to ignore the interactions into materials. We want materials that can take heat and transform it into electricity, light and transform it into electricity, or vice versa. And for that, we need to make work together the spin degrees of freedom, the charge degrees of freedom, the orbital degree of freedom. And indeed, it's very unlikely that we find by trial and error mixing everything in the periodic table what we need. There are strong exceptions to what I'm telling you. In first approximation, graphene, which is a remarkable material, is totally boring and non-interacting. But you know, when it's boring, what do? You stack two layers of graphene, you twist them, and you try to reintroduce the interaction by that technique. So I'm joking a little bit, but what I mean is that in a way, we will not be able to deal without interactions. And there are already materials like the high TC superconductors where people think that this is important. Now, this is a very difficult problem. This is a problem where you get 10 to the 23 particles which are interacting together, which in addition obey the law of quantum mechanics and need to have a wave function which is totally anti-symmetrized. So even the non-interacting problem is not that trivial. And so you can go to very powerful computing techniques. You can do a lot of things, but actually the quantum nature of the problem makes it very difficult to crack numerically with classical computers, and we'll come back to that a little bit later. So I want to emphasize for people or younger students or whoever who have a doubt that this is real science, not engineering. This is a real frontier of knowledge. When you are usually during lectures at universities, people tell you, you go to the infinitely small and you understand what is in the nucleus and what is in the quarks and within the quarks of the quarks and whatever. And that's where one frontier of knowledge is. Or they tell you, you go to infinitely large, general relativity, and this is where another frontier of knowledge is. Well, there is another axis, which is simply the axis of complexity, where you don't change the law of two particles are perfectly well understood, but essentially the fact that you have many, many particles which are interacting together, which makes the difficulty of the problem. And recently, for example, someone like Giorgio Parisi got the Nobel Prize for works in this direction. And this is really where we need very fantastically new ideas, very good techniques, and of course, very good experiments. Okay, so this is the whole field of collective phenomena. So this is a very broad field, and of course, I won't talk about all this, but there is a second pressure which came with various systems, which is to look not at bulk materials, but to look at systems with less and less dimensions. A good excuse is provided by the integration, which tells you that the number of devices is growing, which means the dimension of each device is getting down. Here are some trends if you want to see the size of, I would say, a single transistor in a circuit. But, you know, it's just a motivation to tell you that we need to worry about really, really nanoscale physics. Another thing that people realize is that there is a very interesting physics that exists at the edge of the materials, not the bulk, but the edge is interesting. And I think the first person to really realize this was Bert Alprin, where people looked at systems under a magnetic field, and the Landau level, which corresponds to the quantized quantum mechanical solution in the bulk, are well known and are energy levels separated by gaps. But when you reach the edge of the materials, the energy levels are going up, and so they intersect the Fermi level, which means that at the edge of the material, you get conducting channels, while the bulk of the system is insulating. So the edge of the material can be different from the bulk, and recently people got very interested in things known as the quantum spin Hall effect, topological insulators, topological superconductors, and so on, where indeed what you have is a bulk which is, let's say, boring, which is insulating typically, but you have channels at the edge. So here, if the bulk is two-dimensional, you will have channels, for example, that are one-dimensional at the edge. So all this pushed people to study one-dimensional systems, interacting quantum one-dimensional systems. So there are three urban legends about 1D. The first one is it's a toy model. You use it to understand physics in higher dimension. This is wrong. It doesn't exist in nature. This is only, you know, theoretical, let's say, dreams. And this is also wrong. And I'll try to convince you of this. And finally, when people cannot discourage you to look at this physics with the two first arguments, they say, oh, and everything is understood there anyway, which is also wrong, as you will see. Okay, so I'll try. If there is something you should remember of this seminar is the fact that there is something interesting to do in 1D. So why is 1D special and why is 1D interesting? So think about what is a system which is b-dimensional. You are, let's say, interacting particles in 2 dimensions, and you have infinite repulsion between two of you. You cannot be at the same place at the same time. Nevertheless, you can move very easily as individuals. You just avoid the other people. If you are in 1D, so if you line up at the cafeteria or you go to see a movie or all these pre-COVID, you know, activities that have not totally disappeared, then you will realize that you cannot act as an individual. Because if you have an interaction, then this person will try to move by pushing the person in front, who push the person in front, and so on and so forth. So in 1D, forget individual particle excitation, forget Landau quasi-particles, forget individual aspects, so forget free excitations. Another good example, especially if you come back with a car from Orsay, is the fact that if you stay in your lane, you notice that you have to flow with a flow, so it's a wave which is moving completely in a lane. If you have more than one lane, then one car can recover more or less its individual properties and behave as a free particle. The second is that in 1D, there are strong quantum fluctuations. So all the techniques that you've learned and love, like mean field theory, you know, assuming that something has a good average and you replace operators by average and whatever, this fails miserably in 1D. So you have all the methods that you know go through the garbage can, essentially. So typically, for example, for bosons, if you want to study Bose-Einstein condensation, you say, oh, I have the wave function of a boson, and I assume that it has a finite amplitude, but that the phase is fixed. And then you do expansions around this. In 1D, it will be a catastrophe because it will be very difficult to order. And so 1D has its own physics, its own rules, and its own methods. And fortunately, what we lose on one side, we gained on the other side, and there are very powerful methods. Field theory methods, numerical methods. There is one which is called the Giamarchi density matrix renormalization group that was invented by a guy named Steve White, and also other methods that I won't have time to discuss that are very powerful. But just to show you another example of the specificity of 1D, let me show you what happens two excitations. So I've chosen a very simple Hamiltonian, which is the so-called Heisenberg Hamiltonian, which is spin-spin interaction. And I've started from a ground state here, which is antiferromagnetic, up, down, up, down, up, down, something that Philippe Mendels knows very well, you know, magnetism, localized magnetism. And let me try to create an excitation here. So I flip a spin. If I flip a spin, that's the minimal excitation that I can do. I was at plus 1/2, I go to minus 1/2. So the quantum number of this excitation is 1, -1 if you want. And if I am in 3D, this excitation has a very well, here I created it locally, but in 3D, I can go do Fourier transform, and the energy of this excitation is very well related to the momentum that I put to create the excitation. And this excitation has a name. It's called a magnon. It's the magnetic excitation in a solid. Now, let's do the same thing in 1D. So I will let now the system evolve by this action here. And there are terms as plus, as minus. So I'll flip 2 spins. Then I'll flip 2 spins. Then I'll flip a lot of spins. And you see what happened. If you look at the center, the magnon has disappeared. The magnon is 3 spin down close together. It has disappeared. But what I have here is an excitation that is 2 spin down close together, and here 2 spin down close together. And they are separated by a string of turned spins. So what you see is that in 1D, this magnon has deconfined, it has exploded into 2 more elementary excitations, which shouldn't be possible because delta S equal 1 is the minimum that you can do. But here it's possible because these excitations are non-local. They are not just living here, but they are living here with a string of overturned spin, and that's why they can be created in pair. But if you work out the math, you can check that each one of these excitations carries only a spin 1/2. Which sounds impossible because if you take a spin 1/2 and you flip it, the best you can do is delta SZ equal 1. So it shows you that because of the collective nature of these excitations, you have the possibility to create fractional charges, if you want, in 1 dimension. And in 1 dimension, this is the rule. In higher dimension, this is more the exception, the sort of only case known being the Laughlin quasi-particle in the fractional quantum Hall effect. Okay, so here is a magnon, non-local excitation, which consists in putting 2 spin down together and then turning all the spins in the wrong direction. So questions, how do you observe this? All probes are local probes. So how do you observe a non-local excitation? Well, okay. You have, of course, hidden topological order parameters because the boundary here is very well separated from the boundary here. So I would say topological nature of an excitation is the norm in 1D. You could view it by the phase of the spins here. You could say this has phase 0, this has phase pi, and you see that the boundary condition here, phase 0, is different topologically from the boundary condition here, phase pi. You have continua of excitations because you can split, for example, the energy, the momentum of an excitation, the magnon, into 2 sub-excitations. So instead of having a well-defined relation between the momentum and the energy, you can spread the momentum and each one of the spin-on will have its own energy. So instead of a nice momentum energy, so a particle, if you want, dispersion, what you get is a nice continuum of excitation. This is the total momentum, and this is the total energy, and potentially you can reach all this energy level. This is called as the de Cloiseau-Pearson continuum. Okay. If you have both charge and spin, same phenomenon occur. Let me remove one particle and you remove a charge and a spin. If you have electrons, for example, and then after a while, I let the system evolve, and you will see that there is a place where there is no charge missing, but there are 2 spin down. This is the spin on that we saw before. But if I let the charge move, for example, you see that now, after a while, there is a place in the material where there is 1 charge missing, but the spin environment is up, down, up, down, up, down. So in a way, there is no spin missing here. And this is an excitation that carries only charge degrees of freedom. So again, the electron has fractionalized into a holon. I'm not responsible for the name, so bear with me. Holon, which carries the charge, and the spinon, which carries the spin. And that's only possible because, again, these are non-local excitations, which have a string of spin which are turned in the wrong direction between the spinon and the holon. But if you're strictly in 1D, there is no force that prevents you from deconfining. In addition, there are a lot of very beautiful theory properties that I will not insist too much. You get Paolo decay of the correlation functions, and the person who really did fantastic works in this direction is Duncan Haldane, who got the Nobel Prize for other but related works. So for example, here I show you some correlation functions, like you create a boson at point 0, you try to destroy it at point x, and you will find that this object decreases as a Paolo with an exponent which depends on the interaction. So this is a remarkable set of properties which went through the name of Tomonaga-Luttinger liquid, which replaces what is the Fermi liquid in 1 dimension. And this sounds much more like a system at the poise of a phase transition or in a critical state than a system made of individual particles. So this is all very interesting and very beautiful, but does it exist? That's the first question that one could ask. And of course, the place where you can look for such physics is condensed matter. That's where we are. And of course, that's the lab where to discuss this, because in this very lab, in the 80s, using crystals that were synthesized by Klaus Beckgard, essentially the team of Denis Jérôme here in 1980 showed that this molecule, which is called tetramethyl tetraselenea fulvalene, I trained very hard, you know, to be able to say it. Otherwise, you know, it was a very, very strong activity of the lab in the 80s, believe me. So this is TMTSF, and there is a parent molecule called TMTTF, which are molecules which are stacked on the top of each other. So the conduction of electrons is mostly through the stack, perpendicular to the screen, and very difficult for the particle to hop from one stack to the next. So this is quasi-1D organic conductors. And what was spectacular was that these conductors have a superconducting phase. Here is their phase diagram under pressure. Okay, TC is rather low. It's about, let's say, 2 Kelvin. So at the time, it was believed that this was maybe a route to high temperature superconductivity through organics. But who cares? It's not important. What is important is that this is a quasi-1D system. This superconducting phase, nobody knows really how it works. So this is a mechanism that is probably non-trivial BCS. It has an antiferromagnetic phase or spin density wave. It has a spin piles, which is non-magnetic phase. And it has a metallic phase, which is very, 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 very weird. And lo and behold, when you analyze this metallic phase, these are experiments of optical conductivity done in the group of George Gruner by Leo De Giorgi and Martin Dressel. You find that there is a peak in the optical conductivity. And if you believe in Luttinger liquid theory, you can check that what you expect is a tail, which is a Paolo. I told you there are Paolos everywhere in 1D systems. You can expect a Paolo, and lo and behold, when you fit this part, you get essentially a Paolo. So this was an experiment that clearly demonstrated, to the best of my knowledge, it was the first experiment on a metallic system that showed the existence of Tomonaga-Luttinger liquids. So this exists. Shortly after came the nanotubes, the carbon nanotubes. Now, for the younger generation, you would call it a wrapped up graphene sheet. But this was before graphene. So this is indeed a wrapped up graphene sheet, very long and very atomically broad. So this is a perfect one-dimensional system. These are false color image from the group of Kesdecker. And if you look at the transport through this structure, you again expect power laws. And I won't go into the detail, but here is the temperature. You don't see the axis, but the temperature versus conductance. And you see very clearly in a log-log, in a log plot, you see very clearly the power law that people have interpreted as Luttinger liquid physics. There is some debate on this interpretation, but I don't want to discuss it. How do you see the fractionalization? As much as seeing power laws is easy, as we discussed, seeing the fractionalization, remember you get only local probes. So seeing the structure with a string is a little bit difficult in condensed matter, but you can, for example, do neutron scattering experiment. And if you do neutron scattering experiment, you measure the spin-spin correlation function as a function of its energy and as a function of its momentum. And here are results obtained by Christian Ruegg at the PSI, the Paul Scherrer Institute. And you see very well that you have intensity, clearly not stacking up in one finite region, one line in the energy momentum space. And you see also that if you compare the experiment with theoretical prediction that were done by Jean-Sébastien Coe in Amsterdam, this is a very good agreement between the two. So you don't see the fractionalization, but you can explore the consequence of it by seeing that you get continua instead of single particle excitation. Here is another system done in the group of Amir Yacobi, then in Weissman, now in Harvard, where he uses quantum wires, which are extremely thin and narrow, let's say, semiconducting wires, which are essentially a good realization of 1D systems. And putting a magnetic field, he can do controlled tunneling between the contact here to the wire and back, and do spectroscopy and explore essentially the possibility to tunnel. And the claim is that if you have two excitations which are independent, one which carries the spin and one which carries the charge, they will have two different velocities. So you should see two peaks here in the tunneling. It's very difficult to see, but they did a smarter experiment. They did an interference using the finite length of the wire, and essentially they see moiré pattern, and also not the moiré in graphene, but moiré directly coming through the experiment. And this was, the theory was done by Jaroslav Cherkovniak and Bert Alprin. And I would say this is convincing thing that indeed they saw what they claim they saw. And there are many others that I don't have time to discuss. So what's new in the 21st century? You could say all this, this was the 20th century and people had understood everything. And actually there was a complete drastic evolution of the 1D world. First, there were new methods. People developed remarkable numerical methods. I already mentioned the DMRG, density matrix renormalization group. This was invented in 1990, but got a boost on steroids in 2005 or so, because people realized they could do dynamics. They could measure out of equilibrium. They could measure time-dependent correlations with this. People managed to compute correlation from a method which is a little bit harsh, which is called the Bethe-Ansatz. And this was also a big progress. But more importantly, there were a whole class of new systems that arrived, cold atoms, new species of magnetic insulators and so on, that gave a tremendous boost to the field. And of course, people ask new questions, like what happens if you have strong spin-orbit coupling? This is all the field of essentially topological insulators. What happens if you put the system out of equilibrium? So far, what I showed you were equilibrium systems, but all these systems now can be easily put out of equilibrium. So here is a new experimental system. So cold atoms. So cold atoms, this looks like this. Go to the Institut Optique here, not too far, and you will see experiments like this. And with that, you can realize 1D systems. For example, here is an experiment in the group of Jörg Schmidtmeyer in Vienna, where he uses atom chips to trap atoms in what is a 1D tube that is then splitted into, and then he let it fall. And when it falls, it creates an interference pattern. And by illuminating, he can measure the interference. And this is a direct measure of the correlation function, of the single particle correlation function. And that you can try to see if it works reasonably well with Luttinger liquid theory. And the theory was done by the late Adilet Imambekov, Gritsev, and Eugene Demler. And this is very satisfactorily explained in terms of Tomonaga-Luttinger liquid. So this is one very nice system. Here is a study that was done in another group in Texas, the group of Randy Hewlett at Rice University, and we helped a little bit. Piotr Grisin was the main actor here for the theory. What Randy managed to measure in this system, so he realizes tubes of fermions, but it's a tube of fermions where when you turn a knob, you change the interaction. So this is the wonder of cold atoms, that you have a perfect control on the interaction. And therefore, you can measure the velocity of the excitations. And here is the experiment, and the theory is the dashed line of the velocity of, if you want, the sound velocity in this system as a function of the strength of the interaction. And that's, of course, something which is a little bit harder to do in the condensed matter context. Yeah, there was a kind of popular journal who said ultra-cold atom confirmed 50-year-old physics theory. I don't know if it was a compliment or an insult, but okay, I'll take it as a compliment. How do you test the spin-charge separation? Well, now you have the possibility to image the whole system. Imagine, like here in this room, taking a photo of atoms. A single realization. Not an average, single realization. That's what people know how to do. This is images coming from the group of Immanuel Bloch in Munich, where what you see here is a photo of a single chain. They have been split here, but this is technical convenience. Forget about this. When you see something in the bottom row, it's a spin down. When you see something in the top row, it's a spin up. When you see nothing, it means a hole. And so they can take a snapshot of the configuration, which corresponds to this spin orientation. And because they see the whole configuration, now they can probe for string order parameter. So this is something that they used to test for the spin charge separation and check that indeed the little cartoons I showed you before were there, and that the theory was behaving the way it should. There is, by the way, in the group of Randy Hewlett, another paper that was published in, let's say, a gossip journal. No, I mean, one of the very prestigious journal, Science, where essentially they manage also to measure the spin velocity and check that indeed they have spin charge separation. Okay, there are new theories. You can do things that people were not able to do by combining methods. So you can combine field theory, for example, which are usually very efficient at large distance, long time, small energy scales, but which suffers the fact that you have to inject in a field theory parameters you don't know. With numerics, and numerics is usually efficient at short time, short distance, but usually then you can compute everything. And one of the great difficulties is to make these two theories work together. And in the last, let's say, 15 years, we managed to do this in one dimension. And therefore, we have, by combining this technique, the possibility to fully go from the microscopic model to physical observable at arbitrary energy scale. And let me just show you an example. Okay, maybe I won't discuss too much this one, but this is a spin ladder. So this is a system where you get copper sites which carry a spin 1/2. So this is an insulating material which has magnetic properties. And here is a paper done in the group of the late Claude Berthier by Martin Klemsek, where this material has a natural ladder shape where the exchange are about 12 Kelvin in this direction, 3 Kelvin in this direction, and only 50 millikelvin in the connecting one ladder to the other. And so you can use these techniques to extract from the field theory expression. This is the NMR relaxation time, for example. But normally, this is a function of a lot of parameters you don't know, like this K here, the velocity U, and so on. And using the numerics, you can compute these parameters from the microscopic model. And here is the result. The dots are the experiment. The red line is the result of this formula without adjustable parameter. So this is the first time in my life that I can fit an experiment in condensed matter without any adjustable parameter. So this is, I think, something which is remarkable. Okay, so we get quantitative agreement with the predictions of the Luttinger liquid. So is it the end of the story? Is it the last thing that I said, oh, everything is understood anyway? And I have 10 minutes, so I'll try to convince you in these 10 minutes that now, you know, the real shit begins. Because now we are in a position where Fermi liquids were in the 60s. We understand this, but we can build on the top of this and discover the transistor superconductivity and the giant magnetoresistance. So this is where the fun is. And so we'll boldly go where no theorist has gone before, and we'll try to go beyond Luttinger liquids. So again, this is a couple of examples. Just like with Fermi liquids, you add perturbation. Instead of the vibrations of the lattice, you can add the lattice itself. It creates Mott insulator. You can add disorder. It creates the Bose glass that Mark didn't mention, but this was one of the work we did with Hein Schulz. He told you about the Bragg glass, which is another one. But this is fun. Take bosons and put them in a random potential, and you get a fantastic phase, which is localized and interacting. Multi-component mixtures. You can have new types of quantum critical points. And we all know the importance of topology. Again, Duncan Haldane, but also David Thouless and Michael Kostelitz got the Nobel Prize for this type of research. Transport out of equilibrium situations. So let me just show you a couple of fun experiments in the field of cold atoms that we could bash our heads on, and which are just the tip of the iceberg. So for example, in the group of Tillman Esslinger in Zurich, and Martin Lebras is the person who did the experiment, they could realize a wire here where they put by lasers a periodic potential. So you see here a kind of artistic view of the system. And here is a big reservoir, and here is another big reservoir. So they can do transport through a 1D structure where there is a potential. And the point is that they can tune the interaction at will. So these curves are various interactions. Non-interacting is essentially here. Infinitely attractive is essentially here. And you see that essentially these are the same curve. This is very weird. It looks like when the system becomes superconducting, it still conducts exactly the same way. Why? I let you read the paper to have an idea of the answer. Hall effect. Hall effect, and that's the second example I will take. It's something you all know in condensed matter. You put a magnetic field, you put a bar here, you pass a current, and you measure the Hall voltage on the edge of the system. When it's non-interacting, the urban legend is that it's measured the inverse of the number of carriers. Actually, it practically never measures the inverse of the number of carriers. It measures some integral of the curvature of the Fermi surface, and this is a topological invariant, and this is the famous Thouless-Komoto formula for which Thouless got a part of his Nobel Prize. But with interactions, what is the Hall effect measuring? This is a completely open question. I'm not talking about the quantized Hall effect at very strong magnetic field. I'm talking about the boring, small field, you know, the plain vanilla Hall effect. Compute it with interactions. I won't show the curve, but if you ask me, I'll show it. There were measurements done in this very lab on the organics of the Hall effect done by Joël Moser and Denis Jérôme. And these experiments give some temperature dependence of the Hall effect in the Luttinger liquid. The problem is that there is another measurement done in the group of Laszlo Foro in Lausanne with the same compound, which gave a totally different result. So here is a recent experiment, which was done in the group of Leonardo Falani, who is here in Florence. And we did the theory together with Michele Filippone, Cécile Repellin, and Sebastian Grechner on the Hall effect. So what they have is a ladder of atoms here in which they put a quote magnetic field. I say quote because atoms are neutrals. So it's not a real magnetic field, but it's a fake magnetic field using Raman pulses. And they pass a current by giving a kick to the system. So this is the artistic view, but these are real data from the experiment. You see the momentum is definitely more forward than backward. And you see that the population on this side is not the same size, you see it by eye, than the population on the other side. And therefore, you can use this experiment to measure the Hall effect. And lo and behold, in some of the regimes where we can do the calculation, it fits the prediction that we have. In the other regimes here, note the theory here and the experiment there. We are totally unable to compute the thing here. So it's not because it's 1D that you know how to do everything, far from it, but at least you have a stepping stone coming from the Luttinger liquid to build your theory. You can want to go to more than 1D by coupling 1D chains. Let's look at the spin charge separation that I mentioned. Now I do the same thing and I'll accelerate a little bit. And I let the charge move and I accelerate a little bit. You see that now the string, which was before not costing anything, is now costing a lot because of the presence of the other chains. And therefore the charge and the spin are confined. And that's the Landau quasi-particle. How you pass from a 1D situation to a 3D or 2D situation, this is what people call the dimensional crossover. And this is a very, very difficult question. Here is some data measuring the excitation of this string, not between a spin-on and a Hall-on, but between two spin-on in a recent material, which was called Bakovo. And this experiment are done in the group of Béatrice Grenier and Virginie Simonet and Vincent Petit. And it's very emotional for me to work with them. I hope they are not listening. I got them as students in the DEA de Physique des Solides. So this is, So you have a string which confined two particles. You know the solution. It's like the hydrogen atom. You get resonant energy levels. You see the energy levels in the neutron scattering experiment. And here is the probe as a function of the energy. This is the intensity. And you can calibrate your theory by checking that you can reproduce correctly these excitations. The organics. We started from the organics. We'll finish by the organics. I told you that they are 1D, but of course there is a little hopping between the chains. And all this phase diagram here is below the temperature at which the system has gone from purely 1D to 2D and then 3D. So if you want to understand the organics, it's not enough to understand Tomonaga-Luttinger liquid, 1D physics, but you need to understand how you go from 1D to a very strongly correlated 2D or 3D systems. And there are a lot of ways you can try to do theories. You notice that this is all dashed line, which means this is theoretical bullshit, essentially, because otherwise you put a solid line. But essentially, this is the idea that you will go from a Mott insulator to a high dimensional metal, which is correlated. But we are struggling very deeply with numerical methods, with techniques to try to understand this. Here are experiments that were done in this very lab to probe the energy scale of this problem. And you see at least it's consistent with what was the schematic phase diagram that I showed you with this. You can study materials in contact with a bath. You can say I have a 1D chain and the rest of the universe is a bath, or I put a real bath. And these are studies that are ongoing and which are very, very complicated. Here is a very recent paper trying to attack by numerical techniques what happens when you have a 1D chain which is in contact with a bath. You can study transport when you have losses of particles. This is an out of equilibrium situation. And we also do not know really how to completely attack this phenomenon. And finally, you can study transport in 1D structure, subjected to noise, time-dependent noise, and this is also a case for which we are really struggling with the physics of this system. So I think my time is up, and Swiss accuracy. Or cold atom accuracy, 3 seconds accuracy since the beginning of the age of the universe. That's what the atomic clocks are able to do. Okay, so conclusion. 1D theory can be attacked by a lot of methods, and all this contributed to develop the replacement of the Fermi liquid theory, which is called the Tomonaga single liquid theory. And what is important is that this theory works. It explains many experiments, but more importantly, it allows you to go beyond. It's something which allows you now to attack really powerful, beautiful, and challenging questions which go beyond the Lagrange liquid and which are important not only in 1D, but also to understand the 2D or the 3D work. We need interplay of analytic and numerical technique, and we, of course, need new ideas to make progress. And what is really beautiful in 1D is that there are now many experimental realizations, both in condensed matter and in cold atoms, so we can take the best of both worlds to really make progress, test technique, and of course, have new challenging problems. There are a lot of open questions. I just listed a couple of them here, and I don't want to repeat what I just said, but I just added the dimensional crossover here. How to go from 1D to 2D or 3D is a kind of the challenge that really is waiting for us in the next, let's say, 20 years or 30 years, and we need you, I would say, to be able to address this challenge. So I'll conclude with this slide of Calvin and Hobbes, which I like very much. And it says it's a magical world, or Hobbes all body. Let's go exploring. And on that, I'll stop, and I thank you for your attention.
Thank you, Thierry. Merci.
Si.
So are there questions from the audience? Wow. Okay, so let me shoot first.
Okay, vas-y.
So you said that one of the challenges is a way to go from lower dimensions to higher dimensions. The question is, if you do the reverse.
Yes.
So you go from higher to lower, is there a meeting point? So
that's very difficult to really answer this question. If we take the Hubbard model, I would say it has been solved in 1D and infinite D, and by using DMFT. So the problem is that probably the most interesting dimension is D equal 2, and meeting there is very difficult. So creating 2D or 3D by coupling 1D chains like this is something that we are trying very hard at the moment, using the fact that we know fully the solution for the 1D chain. The problem is that the coupling is relevant, changes the physics, and the numerical methods blow up in our face when we try to do this. So we have to invent ways of circumventing this. They have the same problem when they go from, let's say, infinite dimension to try to go down. And the idea is that in infinite dimension, you can be happy with one site. If you want to do better, you need to put a cluster. And we did with Antoine, for example, Antoine Georges, the cluster, which was a single chain. And there you can say it's a compromise between what we know from 1D and what we know from the dynamical mean field theory. But that's the very challenge that one has to face, is how to meet somewhere in the middle. And I would say we fail for different reasons in trying to do this at the moment. So how it will work, I don't know. But I think that's an active challenge that people have to address. And for that, again, the more experiment we have, the better, because the experiment allows you to benchmark approximation or techniques that you try to use. Yeah. So for one-dimensional systems, yes, this is the result of a long sequence of theoretical studies that started actually with people like Tomonaga. So really the 1960s, before I was even born. Then there was a lot of activities in the 70s, notably two people, Alan Luther and Vic Emery, and building on field theory methods, you can show that you expect this power law. And what was the remarkable contribution of Duncan Haldane was to show that actually this is not an approximate feature, because Emery and Luther did a lot of approximation to reach this solution, but that this is the sort of exact low energy behavior of the system. And he gave a recipe by which you can even compute the exponents of this power law. So we understand why there is the power law. If you want, imagine a system, if you have a system which undergoes a phase transition, you know that at the critical point, your system has power laws. Well, view the 1D system as a system which is on the poise of a phase transition at t equals 0 due to quantum fluctuations. And therefore, it has power laws in practically all the quantities you can imagine. Not all, but a good part of them. But technically, we can compute them. We know why they are there. What, of course, we don't know is what happens in more complicated problems like disordered systems and things like this, or when we couple 1D units.
Yes. Oh.
Yes.
There are XFL now allowing from time because orbital and electronic dynamics at the femtosecond time scale. Do you have any ideas about what would be interesting from one or this data?
Oh yeah, there are a lot of beautiful experiments that could be done. One of my favorite, but because it's emotional, we know that in 1D there are, for example, spin piles transitions. So you have chains which dimerize and give you a non-magnetic phase. You could easily imagine exciting the degree of freedom that corresponds to the dimerization, and then measure how you go from the gap phase in a spin piles phase to the antiferromagnetic one. So there are many experiments that corresponds to out of equilibrium 1D systems. Some of them have been done in the cold atom world, but you have to realize that for cold atoms, the temperature measured in units of the Fermi temperature is 1/10 or 1/20. So it's like if in condensed matter, one was doing an experiment at 1000 Kelvin. So there is a lot of room for improvement. But on the other hand, this possibility of doing out of equilibrium physics is really nice. But now with indeed free electron lasers and so on. So if you want one, a good quench on the dimerization of one chain and measuring the response of the system would be a fantastic, I think, experiment. If it can be measured, yes. That would be the response in time as a function of time on how the correlation function evolved from something which is antiferromagnetic to something, if you dimerize the chain, you make singlets, so they become non-magnetic, they decrease exponentially. And how the evolution in time of this correlation function would be, nobody knows, and computing this is again challenging at long time. At short time, we can use the MRG, we can use these numerical techniques, but we lose the possibility to compute something like 20 times the inverse of the exchange magnetic constant. For the experiment I was mentioning, it would be in the spin channel. It's in the spin-spin correlation functions. But one can imagine similar experiments for electronic systems. If you want another one, I would already love to see the Hall effect experiments redone to know finally, 20 years after, what is the Hall effect in an organic superconductor.
I can do it later privately. I mean, it's
no problem. Yeah.
okay. It's okay.
Thank you very much.